This is lesson 2.1.8, interpreting graphs. So previous to today, you have learned how to graph basic linear equations on a graph. You've learned how to find the y-intercept and the slope. And now we'll be learning how to interpret what those mean in some contextual examples. So our objectives are to interpret the relationship between two variables in a graph. Our two variables are x and y. And then we will graph and interpret some functions. In this first example, the graph shows the volume of air in a balloon as you blow it up until it pops. So take a minute and look at our graph. Here's our essential questions. What are the variables in this graph? Remember that we described the variables as x and y, so think about where x and y are, and that will help you to identify the variables. Second question, describe how the variables are related at various points on the graph. So what that means is, how do these variables relate here? Notice how the graph changes. It goes up and then changes steepness. And then again here, it changes steepness again, and etc. all the way up to here. And then what is going on between here and all the way down here? So that's what we are going to be describing. And then our final question, does the person blowing up the balloon pause the same amount of time for each breath? And explain how we know that. Okay, so obviously if you think about the variables are going to be volume and time. Time representing our x values, our independent variable. It continues on, we don't change it. So time is one of our variables. And then volume is our other variable, that's our y variable, and that changes depending upon time, right? As time goes by, the volume of the balloon, the air inside of it is going to change as the person is blowing up the balloon. So volume is dependent on time. So to answer our questions, what are the variables? We would just say volume and time. Now, describe how the variables are related at various points on the graph. Well, the volume increases each time you blow up the balloon. Picture yourself blowing up a balloon. Every time you pause to take a breath, the volume would remain constant, assuming you had the top of the balloon pinched closed. So, if you think about this graph, starting at the beginning, the person is blowing at a constant rate, pauses, takes a breath here, our volume is not increasing, and then blows again, pauses to take another breath, blows again, pauses for a third time, and then as this person is blowing, what happens to the balloon? Look what the volume is doing. It goes from here, which is pretty high, all the way down to 0. The balloon pops. Okay? And that's how we would explain this graph. Let's look at another example. Here's another graph. It shows board length, and we have some variables labeled here on our graph, and then we have a picture of a graph, kind of looks like a little bit of a step pattern going down, decreasing. So our questions again are, what are our variables? Describe how the variables are related at various points on the graph, and then how many times is the board cut? Okay, and how do I know the board is being cut, first of all, to answer that question? So let's do the easy one first. What are our variables? Well, our variables are length and time. Okay, length is our y variable and time is our x variable. And again, our length of the board is dependent upon time. Number 2, describe how the variables are related at various points in the graph. Well, if we look here, we start off with our maximum length way up here, right? 0 is down here. We have some length up here, which we don't know. But we know that the length of the board remains constant for this period of time until here. And then what happens? Our length drops down. So the only way for the length to get shorter is for the board to be cut, the board to be shortened somehow. So what we have is the board being cut, and then the board remained constant for another period of time. Perhaps the person who's cutting it is readjusting the board in the saw, and then it's cut again, and then it's readjusted, and then it's cut again. So for our third question, how many times is the board cut? The board was cut 3 times, and we can measure that. Here is 1, right there, and 2 being right here, and then our third final time there. All right, good. Let's look at a third example. In this example, here it says June cell phone cost. So again, what are our variables? We will describe how the variables are related at various points on the graph. And then the third question, what does the horizontal portion of the line represent? Right here. So we have to think about that based on what we know with cell phone plans. Okay, the variables, we'll start with that again. Very easy. Our variables are cost and minutes of calls. Our cost depends upon how long we talk, right? So cost is our dependent variable, minutes of calls are our independent variable. All right, 2, describe how the variables are related at various points on the graph. Well, the time right here remains constant for a certain number of minutes, or I should say the cost remains constant. This should actually say cost, so let's change that. Okay, so we changed it to cost. The cost right here remains the same. It remains constant, right? Whatever this value is right here, whether it's $2, 20 cents, it remains constant for a certain number of minutes. We don't know how many, but we know that it remains constant for a certain period of time. And then look what happened. Then it increases. Then it increases. So as far as these variables relating to each other, the cost remains constant for a certain period of time and then increases over time. Okay, so what does the horizontal portion of the line represent? Well, if you think about cell phone plans, the horizontal portion most likely indicates that the cell phone plan provides for a fixed cost, a certain fixed fee, maybe $10 for the first 100 minutes, and then after that you have to pay per minute. Your cost goes up. Okay, so that is what we can interpret the horizontal portion of the line to represent. All right, let's look at a couple of slightly different examples interpreting graphs. In these 2 examples, we'll actually be building some graphs. So here we have a picture and a graph. The picture shows a portion of a bike trail, and here's a biker down here traveling on a flat, and then he's going to climb uphill, and then it flattens out again. And then we have a biker up above who's on a flat spot about to go downhill, and then flattens out again. So what I want you to think about is their speed, because this graph represents the speed of the bikers over time. So our questions here, number 1, we want to explain whether this graph here is a reasonable representation of how the speed might change for the biker at the bottom of the hill. So we've got this biker down here. Does this graph represent the speed that he would travel from here to the top of the hill? So pause this video for a second and think about this graph and think about if it's reasonable. Okay, so when you come back, you hopefully have analyzed this graph and you can see that our speed remains constant over time. And then what happens here? Our speed is getting faster, right? Speed as you go up increases. So this right here might represent 10 miles per hour. But then up here, this point right here might represent 30 miles per hour. Certainly this biker is not going to increase speed as he goes uphill. And then at this certain point here, our speed remains constant, but at a much faster rate than it was down here. So if we look at our answer, we would say no. The graph is not reasonable. The speed should not decrease, or the speed should, decrease as you ride uphill versus increase as this graph is showing. So this graph is not a reasonable representation for our biker at the bottom of the hill. So what we want to do is sketch 2 graphs to represent each biker's speed over time. Okay, now if we think about, we've already talked about the biker at the bottom of the hill, let's talk about the biker at the top of the hill. He is riding at a constant rate up here at the very top, And then what's going to happen when he reaches the hill and goes down? His speed will actually increase. So this graph probably will look more like the biker at the top of the hill. And then when he gets down to the bottom, his speed will even out again, and he may or may not be traveling at the same speed as he started. So let's look at the two graphs. Okay, in this first graph, we have a constant rate of speed, and then the speed drops way down, and then goes back up again, and then remains constant. That represents the biker at the bottom of the hill. So let's think about what he's doing. He is traveling at a constant rate of speed. He gets to the hill and he has to slow way down, maybe to 2 miles per hour. But then as he gets to the top of the hill, he's able to speed back up again and continue on at his same speed before. Notice that we have to show him accelerating back to his regular speed once he reaches the top of the hill. If we were to draw the line down here horizontally, that would say that when he gets to the top of the hill, he continues to travel at the slow rate of speed, the same rate of speed that he traveled to climb up the hill, and that wouldn't make sense. If we look at our second graph here, we are traveling at a constant rate of speed, and then we go very fast. We are increasing in speed this whole time, and then we slow back down and continue on at our constant rate. And that would represent our second biker. And that is very similar to this graph. We have a constant rate of speed. He increases in speed. The problem with this graph, though, is that then it's showing that his maximum speed is what he's going to maintain once he hits the bottom of this hill. So if he were to increase in speed, say, to 40 miles an hour, he would maintain that speed here. And that probably wouldn't be the case. He would probably slow back down and continue on at his same speed prior to that. All right, let's look at one more example. This graph shows the vertical distance traveled as person A walks up a set of stairs. Here's person A. And person B walks up the stairs of a moving escalator. So you can picture an escalator. It moves on its own, and in addition to that, person B is also walking. So if we look at this graph, think about our variables again. Even though it doesn't ask us, our variables will be distance and time. So the distance that somebody travels over a certain period of time. And you can see that person A, his distance does not increase as fast as person B. He covers much greater distance in a shorter period of time. So for example, if I were to mark a point here, and mark that all the way down. After X amount of time, we don't know how long that is, maybe that's 2 minutes, person B would have traveled maybe a distance, if we come over here, of 50 feet. Whereas person A, if we come over and mark where he is, he may have only traveled 30 feet. Okay, so we do know that person B is covering greater distance in the same amount of time as person A. So what we want to do is draw a line. So we're going to draw a line that could represent the vertical distance traveled as person C. So now we have a new person, rides the moving escalator while standing still. So he is also going on the escalator, but he is not walking. He is just standing still. And then we want to explain the reasoning behind our line. So again, think about this, what that line would look like compared to person A and compared to person B. Okay, so let's look at that. I drew the line right in the middle because here's what we know. Person C is still riding the escalator, so is going to cover greater distance over time than person A, but not as much distance as person B. And that would be in our explanation here. Person C would travel at a constant rate. That is faster than person A, but slower than person B. And we'll notice that all these people are traveling at a constant rate. And that concludes our lesson for today.